Alrighty, good evening and welcome everybody. My name is Obi-Wan Pez and this is N Simplex Pachinko. We are doing class tonight, so we have Differential Equations, Night 17. We're going to be working on series solutions. Alright, and we'll have just another minute or so.
Hey, hello.
We have a co-host. Tonight we have enstucky. If you would care to introduce yourself.
Sure. I am Ian Sticky. I'm the host of Mathematical Creature here on Twitch, as well as the organizer for No Royal Road, a geometry study project.
Woohoo! I got really distracted this weekend. Did you post anything?
No.
Okay.
I'm at a one post a week schedule right now, and those are going up on Thursdays.
Awesome. Alrighty, so anybody who would like to, please go see No Royal Road. Put pop your Discord and Twitch in the chat there, and unfortunately Zach will not be able to make it tonight, but good news, he's working on his defense, so we wish Zach all the best for the upcoming doctoral defense, and know that he's going to do great. So,
yeah.
All right. So for tonight, we're doing this. Okay. For tonight, we were talking about series solutions. So, Stucky, coming in from a Calculus 2 perspective, what do you think most students have done at that point?
So in Calc 2, I know we talked about Taylor series, and a little bit of the the theory there, like radius of convergence, right? And so talk a little bit about when these solutions make sense. Yeah. The mechanics are maybe there to talk about Fourier being a sort of power series, but it's not usually. Wouldn't be something that I would expect.
Okay. And so Taylor series falls under the category of special kind of power series. What is kind of the general form for power series?
Like a summation for, and there's coefficients ci times x to the power I. Usually I greater than or equal to 0.
Right, so we can let this go off to n, although I think just generally speaking we let that I go off to infinity. Alright, so we have a generalized power series here. Again, summation of c sub I times x to the I, as I goes from 0 to infinity. So again, very generally this is going to look like c0 plus c1x plus c2x squared, and then this is just going to keep going up forever. So this is going to be a very useful structure for us to use when we're looking at solutions to differential equations, when we're looking at using series. The more specific Taylor series is what?
Oh, sorry.
That's all right.
Oh, when we we ask that there's a function at the start, say f, and then ci is 1 over I factorial times yeah, let's say ith derivative of f evaluated at 0.
And we'll even go one further and say that that's going to be at some initial value. So it can be a, which does not have to necessarily be 0 itself. If it is equal to 0, then there's actually another name for it, or another name that's associated with the series.
Right.
So typically this is called a Maclaurin series, but it's really the same thing. Taylor, Brooke Taylor, there we go, was able to generalize and say, well, we don't have to have it just be 0. It could be literally any point that we want. We just have to shift all of our individual allowed values that we pick. So here, we're going to take the ith derivative of f, our original function, evaluate it at some a, wherever that is, divide by I factorial, and then multiply that by our power term, which in this case is not just x to the I. This one's going to be x minus a raised to the I. So again, we're just taking this thing, and then we're shifting it a to the right, wherever that's going to be. Okay. Anything else you'd like to highlight here?
No, I don't think so.
Okay. And there are some conditions for this. You got to make sure that you can take as many derivatives as you want at that particular point, a comma f at a. But realistically, we're not going to do this with some really weird function. Or if there is something weird going on, like natural log of x, for example, we're not going to be doing this around x equals 0 because it doesn't exist there. So we'll say, okay, I want this to be at x equals 1 for the natural log function, just because that's much easier to work with. All right. And all of its derivatives are very nice at x equals 1 as well. Cool. So when we're looking at this, the other thing that you wanted to bring up was radius of convergence. So what is that?
All right, so this sort of gets at that logarithm example, we don't have a guarantee right off the bat that our this series is going to equal our function at every point, but we do have a guarantee that there is some distance away from A where these two things will agree, assuming the nicety conditions, right?
So we're going to have a distance from x equals a, wherever that initial value is, such that the infinite series, now keep in mind, this is an infinite number of objects. So we're going to add up an infinite number of things, and that is going to converge to a stable value. Some people are like, well, how's that even possible? But again, typically this is done in a Calc 2 class where we're able to see that as long as, if we're very general about it, if we are less than a distance of 1 away from A on this generalized Taylor series, again, in general, that's going to allow us to have terms which will eventually start decreasing in size. The I factorial at the bottom also helps, and we can have an infinite number of terms which, when added up, end up going to 0 fast enough that it doesn't affect higher order terms or higher order decimal places eventually. So we'll say, all right, well, it's good enough as long as we're, a significant number of terms into our Taylor series. And again, most of the time, a distance of 1 away will work nicely, just because here you've got your x equals a term is being raised to a power. So if it's smaller than 1, it's going to get smaller. If it is equivalent to 1, we then have to look at our function and the I factorial, and is it decreasing fast enough and all this other stuff. Okay, cool. All right, well, music went away again. Oh well, we'll have to make do. All right, so if we take for an example, a real simple example. So y prime minus y is equal to 0. We've already done this. We have the solution to this particular differential equation all the way back from the beginning of class. But now we just want to verify that, yeah, we get the right answer if we use these series solutions. So if we were to take this and say, let's let y equal the series as I goes from 0 to infinity of a sub I. Let's be consistent, maybe. C sub I x to the I. So we're just going to do a general power series on this one. We're not going to specifically invoke Taylor series, at least not yet. So what is y prime going to be?
So we're going to differentiate this term by term. So x to c to the I is going to come along for the ride in each term. And then the x to the I will differentiate to I times x to the I minus 1.
Right, so we take our standard setup that we have before, and then we say we differentiate the first term at 0. Second term, we just get C1. Third term, we end up getting 2C2x, 3C, 3x squared, and so on. So yeah. We're always going to have our indices starting from 1 in this case, we'll make it simpler. We could technically start from 0 still, but that's not going to help us out. And then, again, looking at the index on C, the number out front, and the power on X, we end up with an I CI x to the I minus 1. Okay. So if we take that, we can substitute that into the differential equation. All right, and what is your preferred method of doing this?
um, yeah, it's a
I
good
know two
question.
personally, but there are two major
Yeah.
methods.
Um, I like to um I like to fiddle with indices until the um the the exponent of x is the same as the index in the sum.
Okay, so that one is typically called reassignation. So we're going to reassign our indices on our first in order to say, all right, we want our x terms to have the same exponent. That's going to be our major goal. So if we go with reassignation, we're going to say let k be equal to I minus 1. And so we end up with, we're going to leave this, it's going to be in terms of k, but we'll just hang on a minute. What we can do is say that this is going to be x to the k, certainly. And then we say, what is I? Well, if k is going to be I minus 1, then I is going to be k plus 1. So shift that over. We end up with c sub k plus 1 and k plus 1 out front. Just rewrite it. Okay, and then k is going to be equal to, well, in this case, I was 1, so we could do k plus 1 equals 1, and then filter. So here we'd end up with k equals 0 again. Or we could then say, you know what, I don't really like that. I can move I minus 1 equals 0 here, and then directly say, oh, look, k is equal to I minus 1. I know how that works, so k is equal to 0. We're doing the same thing either way. It's just a bit of a game that we play here to juggle things around until things look nicer. Hey, Penn. Hey, Les. How are things going? Good evening and welcome, everybody. If there's anybody in chat who does not know me yet, my name is Obi-Wan Pez, and this is N Simplex Pachinko. We do mathy type stuff on Monday, Tuesday, Wednesday, and gamey stuff on Friday. Currently, we are working with enstucky on differential equations, and we're right now working on a series solution problem So we are letting our fairly simple differential equation at the top, y prime minus 1 equals 0. We just assume that y is going to be a power series. So this is an option. We have our y equals, we have our y prime equals, and then we substituted, and we've done a reassignation to get our variables to have the same exponent. Now, in this particular case, it doesn't really matter what we call the variable because they're the same thing. They're both going from 0 to infinity. Forgot that. And they both have the same terms essentially on the inside. So we can call them both I, we can call them both K. Doesn't really matter. So we could say once again, I equals 0 to infinity is going to be K plus 1, C sub K plus 1 times x to the K. And here we have a minus an entire series. And that series is a whole bunch of addition. So in this case, we can just do it term by term and say like, well, this one is also going to be C. Oh, I did K's. Whoops. All right, I plus 1, C sub I plus 1, and x to the I minus C sub I, x to the I. And all of that whole sum of stuff needs to still be equal to 0 at the end. So this is method 1, and we'll talk about a second method when we get to the end of this one. All right, so in this case, we also have x to the I can be factored out. Beginning or end, right? It doesn't really matter. And then we get I plus 1 times C sub I plus 1 minus C sub I. That has to be equal to 0 when I goes from 0 to infinity. Now, if this entire sum is equal to 0 and it's also essentially a polynomial, what does that mean for us?
Each of the full coefficient attached to xi is going to be equal to 0.
Right, so each coefficient needs to be 0 because x to the I is assumed not to always be 0. It could be 0 occasionally, but certainly not always. So then we're going to say, all right, well, if each coefficient must be 0, then we're going to set that part. So this is going to be I plus 1, C sub I plus 1 is going to be subtracted by C sub I to get us 0, and therefore, did I drop something? No, we're good. Okay. I plus 1 times C sub I plus 1 is going to be equal to C sub I. All right. And then from here, my suggestion would be start with 0. So we can generally like make a table or something. So if we start with I is 0, then we end up with 1 times C sub 1 is going to be equal to C sub 0. 1 is going to imply that 2 times C sub 2 is going to be equal to C sub 1, which is going to be equal to C sub 0. Right, and we want to always bring this back as much as we can to C sub 0, our initial coefficient, which is then going to be able to be used for all of the other terms where possible. It sometimes will not be possible, and that's fine. We'll talk about workarounds when we get to an example. 2 is going to be 3. C sub 3 is going to be equal to C sub 2 which is equal to C sub 0 over 2.
Yeah.
I guess I should have also done a column for the result. Right, so C sub 1 is just equal to C sub 0. C sub 2 is equal to C sub 0 over 2. C sub 3 is going to be equal to C sub 0 over 2 times 3 is going to get us 6. Noticing any patterns so far?
Yeah.
All right, what do we got?
So those numbers on the bottom look like factorials. So I want to write over 1 factorial over 2 factorial, 3 factorial. And,
all right.
yeah.
So it's looking like every individual C sub I is going to be equal to C sub 0 divided by I factorial. So that seems to be a very nice, easy one that we could get for this. This means that we're going to see our power series, y, is going to be equal to, I goes from 0 to infinity, of C sub 0 over I factorial times x to the I. Right. Looking good. Okay. So this also means that we don't actually need C0 inside. I is going to go from 0 to infinity, and we've got x to the I divided by I factorial. This should look somewhat familiar. So anybody who has spent any time doing actual Taylor series has probably seen this on a table somewhere that tells you specifically what this is. But this one's going to be C0 times the quantity, right? So this is just going to be 1 plus x plus x squared over 2. Need more space. Plus x cubed over 6 plus dot dot dot. Yeah, Penn's got it. Right, so this is just y equals C0, so some constant, i.e. our first term in the sequence, times e to the x. I am very happy to see this series, yes. And especially since, right, if you looked at the initial differential equation, y prime minus y is going to be equal to 0. So if we solved it the other way and said y prime is going to be equal to y, right, it becomes pretty obvious. Okay, yes, this was supposed to be one that could be easily verifiable. Right, we know that y is going to be e to the x, just very simply get this one done. Okay. And then if we have a particular initial value, so for instance, so suppose we had an initial value which was right, y at 0 was equal to 3. Then this would allow us to plug in the appropriate value. In this case, our x value is 0, so we know that we don't need to alter a value. From our Taylor series that we were talking about above. So this is our particular a value that we want to plug in for our for the series, like where we're centering our series around, and then the value of the entire series is going to be equal to 3. Now when we go over to our x's to try to plug in the initial value, you notice that x is going to clear out everything, with the exception of our constant term, 1 times the c0 that was outside. So now we just got c0 is equal to 3. All right. Any questions in chat? Anything else you'd like to comment on or explore, Stuki?
I think that's good for me.
Okay. So now more to the point of like why we would ever do this, because this seems like an awful lot of work to solve a first-order linear differential equation, and yes, that is 100% correct, right? You'd never do this intentionally unless you're just trying to prove a point. So for harder differential equations, you might have something that looks like y double prime minus xy is equal to 0. So this still falls under the category of second order linear differential equation. It's ordinary, as always, and homogeneous. So here we might say, well, we didn't actually cover any of the methods to solve second order linear differential equations that have x terms attached to things. Like we did a couple of quick examples with something. Arg. We did a couple of examples with variation of parameters, I think.
Right.
But they don't fit into the nice box of the matrix systems that we were talking about before, just because we have something that is now not a constant coefficient. So since it's not a constant coefficient, it kind of messes things up. So we're going to do the same assumption that we are not actually able to solve this in terms of using previous methods, and we're going to use a series solution to find, hopefully, an exact Taylor series like we just did. If not, well, we have at least an infinite series which will approximate it out as far as we want it to go. And punching, good evening and welcome. I saw you pop in on Discord as well. So you know the elements. All right, so here we're going to do the same thing. So we're going to still, let's also assume that y at 0, so still make it kind of easy, is going to be -4. Don't understand, but here to support. Always welcome. Thank you so much. So differential equations, for anybody who doesn't know, is usually a second-year math majors class. It also falls under the purview of many of the engineering, physics, other physical science classes. So almost everybody within that block, usually computer science, physics, chemistry, engineering, will need to take differential equations at some point. Some of them are able to take other classes instead of differential equations, but it's all at that same level. Depends on where you go. Okay, so we're going to still say let y equal series, and I goes from 0 to infinity of c sub I x to the I. And this time, right, y prime is equal to, same deal as before, this was I times c sub I x to the I minus 1. And what do we get for y double prime?
Well, let's do it again.
Oops.
I times I minus 1. Okay. Hello. Ci x to the I minus 2.
And I left the indices blank on this one because what happens?
Right, so when I is 0 in y prime, for instance, then that's gonna, that I out front is gonna kill that term. So we can choose to start at I equals 1 instead.
Right, so this is the first kind of non-trivial term, the one that's going to actually matter, right? This is our beginning point. All right.
Okay, and so the same thing here. Okay, so now we started with I equals 1, so we don't have to worry about I equals 0, but when I is equal to 1, then again, the I minus 1 out front is going to mean the whole term is 0, and so we can start at 2 instead.
Right. And again, it's a choice to do that. We could just have it start at I equals 0, but it's trivial. So we say, nah, we'll exclude those terms. And this actually works really nicely with the reassignation that we were just talking about, because now we're going to alter all of our exponents to be back to x to the I, and that's going to fix all of our starting indices to be I equals 0 as well. So it realigns everything as well. And let's see, do you want to kick off with this one?
Sure. So
if your setup is good to write with.
Yeah, it took a while, but we did get there.
All right.
So I'm going to take k starting at 0 by choosing k is equal to I minus 2 equals sign, I promise. Okay, and so then I is equal to k plus 2. I minus 1 is equal to k plus 1 plus 2.
Stu, I'm going to just check something real quick, but...
For sure.
Doing great.
Okay, and I'm gonna stop there because in our differential equation, we're not actually gonna use y prime. So deal these two formulas, and get that.
Sorry, it sounded suspiciously like something fell out of bed, but... Given that one of my children is 6 foot up in the air.
It's important to check.
Yeah.
So let's take I goes from 0. Okay, let me be a little bit more cautious here. I'm happy with that rewriting. So let me copy that down. So y double prime is equal to what we just wrote. And then we're going to subtract x times I equals 0. Ci x I. I'm going to move that x inside okay. And now I want to rejigger again because that x being inside has meant that we now have disagreement between the variable and the exponent.
Mm-hmm.
So take keep going in red. So I'm gonna make j is equal to I plus 1. So then we're gonna get c. So I is equal to j minus 1. X to the j. And if I starts at 0, then j starts at 1. Okay. So we'd like to add these things together, but the orange one starts at 0 and the red one starts at 1. So we're going to fix this by splitting off the k equals 0 term from the orange.
Yeah. And so that was also, for anybody who hasn't seen this before, that's the other method that I was hinting at the beginning. Other than reassignation, you can burn off individual terms until you make your indices agree with each other. And so we just take off the first number of terms until they match. The problem with that one, if you start with that at the beginning, is that our exponents don't match. So you do end up with something that's just a little bit off, but at the same time, you could figure it out. It's not terribly difficult.
Yeah, without thinking, I imagine you could sort of do these in the other order if you wanted. But perhaps that you might run into issues. I don't know.
Well, there's always going to be a slight issue anytime you end up with, as you had said over here, your index doesn't agree with your um, exponent, or at the very least, what is it? The indices and the exponents don't both agree with each other slash themselves. If they're exactly the same distance apart, it's not an issue. You fix it.
Sure.
And this is one of those topics where you just say, well, you're going to have to kind of figure all this out as you go. Um, Eventually, you run into a new example. You're like, wow, don't think I've ever seen something like this before. And then you say, okay, well, let's fall back to our toolbox. And what was it that we did for some other examples? Okay, let's try these. Let's try these examples out and see, or try these particular methods out and see what gets us to a nicer position. So it doesn't have to be anything that you've necessarily understood or 100% done before. And some students out there might be panicking about that. But if you run across a new novel problem that you've never seen anything like it before, just kind of poke at it for a while. See what happens if you try some of your old methods that you know. This is why we say that math can be fun, and people don't believe us. I mean, I shouldn't say that, right? People do believe us, but.
So checking
All right.
checking this work.
And all of that is going to be equal to 0, just as it was before.
Okay. Um, then let's maybe make so the equation here is going to be since we need all of our coefficients to be 0.
C sub I minus 1. Think that last one.
Yeah. Okay, so probably I want to rewrite that somehow, but let me get started first. So this is 3 times 2. That's 6. C3. Minus C0 is equal to 0. Hey, that's convenient. Although I'm not sure it's a good kind of convenient. Let's keep going. Okay, so 2, the 6 is going to turn into a 4 times 3, which is 12. C4 minus C1 equal to 0. And I'm really excited to get the next one because that's a number I've seen before. Okay, so 3 plus 2 is 5 times 4 is 20 times C5. Okay, and then, yeah, as you noted, got our C2 is equal to 0.
Right, so anybody who isn't seeing it right now, we have an x to the 0 term that's here. We just don't usually write it. And you're not going to get an x to the 0 out of the summation at all, since we started with I equals 1. So because we don't get x to the 0, then this is going to be a standalone term, 2c2. You don't have anything else anywhere else, so it's got to be equal to 0 itself, so therefore c2 is equal to 0. All right, what are the implications then?
So, well, I guess that we now can make that third one look a lot better because that's just 20 times C5 is equal to 0. So C5 is 0.
Yep. Pop that to the right there. Yoink.
Okay. That feels handy, but I'm not quite sure I see it. But I guess what comes to mind is that I'm expecting there to be two constants because it's the second order equation. So I'm never going to see C0 or C1 again because the indices are just going to keep increasing. So I kind of wanted those to be my base. So let me...
Yeah. So C3 and C4 are both going to be based on C0 and C1. And then when we move out from there, C6 is then going to be based off of, 3 back, right? So C3, which is based off of C0.
Right. Or C1. Yeah, so let me... Okay, so these are probably numbers that I should know off the top of my head, but I don't. C6 minus C3.
Product of two adjacent numbers, you mean?
Yeah.
I mean, it's quadratic, right?
It is quadratic.
So realistically, we're just adding, yeah.
I see you're goading me into into doing second order differences. Okay, so this is 8 times 56, C8 minus C4, C5. Okay. Well, C5 is 0, so so C8 is also 0. And I think, right, so C6 depends on C3. Which is some terrible number times C0, C7.
I mean...
Yeah, or 64. Sure, I'm just gonna write it down. Um, okay. But as you're pointing out, so I don't know what these terrible numbers are, but um, I see that they somehow we've things are separating nicely. Um, like it's since it only depends on the thing that happened three earlier, then we can sort of uh, group these um, into the ones that are the multiples of 3, which are all going to come back to C0, ones that are 1 more than a multiple of 3, which are all going to come back to C1, and the ones that are 2 more than a multiple of 3, which are going to be 0, because they come back to C3, or C2, sorry.
Right. So in theory, right, we've got a general solution that looks something like this.
Right.
You correctly pointed out we've got a C0 times some summation. You could take all of those individual terms and just add them up with the appropriate um, exponents. And also do the same for C1. So all of our C1s end up being these particular numbers, and they have x's with this particular exponent. So, yeah, that works at least somewhat nicely as like a generalized, here's what the solution is going to look like. I don't actually know what the solution is in this particular case. I don't think there's going to be a really nice pattern to it, but it exists. And we don't necessarily need a nice explicitly defined pattern. It's okay if it's implicitly defined, just as what we've been doing here. We'll just say like, okay, these are the values I get. It's going to go off toward infinity. Good luck. Um, that's not implicitly defined. That's still explicitly defined. It's just that we don't have an expression in I. Um, I don't think it would actually be terribly difficult to find this, given the other values that we've got here, but like we don't have to continue. So this will
Oh.
be, this will be good enough if we just say, here's what it looks like. We are coming up on an ad break, so I think this is a good place to pause for a few minutes, let people grab water, stand up and stretch, do what you need to. I think I'm going to just write these two solutions out in their grouped form, and then we'll be back after that to do another example that's going to be a little bit more involved.
Okay.
All right, so see you all back in about 3 minutes. Thank you so much for coming, and more differential equations to come. All righty. See you in a couple.
All right. Will do.
All right, and we are back. Thanks everybody for sticking around, supporting the channel, doing all that stuff. Um, we'll be taking another break in 1 hour. That's going to be our official end time for class, and I may or may not continue, I guess, after that point. Depends on how we're feeling. So we'll probably open the floor after class for other math questions. So anybody who is uh, not a differential equation student, again, feel free to stick around, but most likely we'll probably have a little bit at the end, at least for any sort of questions you want about anything in mathematics. Um, so a little bit about me, I guess. I've been teaching at a community college in Maryland for 15 years prior to moving to the UK, which we're now in the UK. And I'm trying to figure out what I want to do with my life. So I've joined up with the Elements, which is this crew of really awesome termed math chads. Thank you, Penn Center, for that name. At least I think, right?
I think so. Maybe it was Danny.
Yeah, that tracks. um, so anyway, yeah, uh, we've been just hanging out and trying to figure out some good ways to further mathematics and math teaching. So, working on Twitch seems like a really awesome deal for us because I get to teach math to anybody. So, again, thanks everybody for coming in, and we're going back into our differential equations for this series solution. All right, so we've got our C0 times 1 plus 1/6 x to the third plus 1/180th x to the sixth, etc. So here we can at least point out the fact that we do have a fairly nice summation where our exponents are going to be multiples of 3. So we could do something like this where every time we tick up 1 to get a new term, we're just going to have it be 3i. And we could also do it as 3 parentheses I minus 1 and start with I equals 1. I'm not particularly committed to one of these results over the other. I believe 0 is going to make this slightly easier at the beginning. Not exactly sure how this is going to work myself. Yeah. So like
Yeah,
it's going to start rolling, right? It's picking up the previous 2 terms that we got at the bottom in the denominator, and then it's also picking up the next 2 terms in the next one that we got. So, yeah, this is probably not going to be nice. Uh, although, in theory, this is 6 factorial over 4.
right. The problem is the denominators just don't turn into factorials very nicely.
3
Um,
factorial over 1. And that's just, yeah, that's not going to work. It's worth a shot anyway. Right, because I want this to be like probably I squared or something. No, it's not going to be I squared. It's just every 3. It's back 2 from wherever we are. So like this doesn't work with that particularly well. We might be able to start our series after the first term, but then again, it's going to kind of be like, okay, but I'd much prefer this to be all-inclusive if we can. So, in theory, right, it could be something like our 3i factorial 1 over. Right, parentheses 3i factorial. And then up top we'd have like I minus 2. But then that's going to also pick up on the next one as well. Yeah. Well, it was worth a shot anyway.
Worth a shot.
This is also, you could see professional mathematicians at work here. So this is how we actually do stuff. We just kind of noodle around for a while and see what happens. Nope, nope. So if, in theory, this works out as a summation, then we could just end it and say we're going to do the same with C1 and then work out the same issues that we've got here. So like this is 5's going to be missing here. We're probably going to have 2 missing on the next one, etc., etc. Our exponents on this one are going to be off by 3, so we're still going to get x to the 3, but in this case it's going to be I plus 1 on the inside. Summed up. Again, maybe I goes from 1 to infinity with the first term taken off. So it's x plus, get all that, and some coefficient up front. So I suspect this is probably how it works, but I don't have a nice version for this. So most differential equations classes, the teacher's going to be perfectly happy to have you stop here. And also, if you notice, this is a second order differential equation, and we have 2 linearly independent solutions. So this fits in very nicely with what we were talking about for all second order differential equations. We're going to have, whatever ordered derivative we're taking, it's going to be that many linearly independent solutions for our answer. So if we have a fourth order derivative, we're going to get C0, C1, C2, C3 as our 4 coefficients out front, most likely. It may not work out 100% that way, but depending on the intricacies of the individual solution you've got, it's most likely going to be that you're going to have 4 solutions, each of which starts with the first 4 coefficients of the series. I guess I can caveat that by saying, like, if there's any terms that are just plain missing, right, then obviously we're not going to use those to start any new solutions. Alrighty. Let's... There we go. 1 plus x squared, y double prime, minus 4x, y prime, plus 6y is equal to 0. And I don't think... Right. Y of 0 we're going to have be 2. And y prime at 0 we're going to have be 3. So, where do we want to start?
Well, uh, we want to choose a series for y, and then compute its derivatives. But we did that already, so I'm going to steal it.
Yep.
Um,
Right.
okay.
In this particular case, it's not plagiarism, it's citation.
I don't know how to do this though, actually.
Here, I can snag. Yeah, looks like you might have it.
No, I can't figure out how to copy it.
Oh, I just did Control C. But I'm
That's
also
not
on
as...
PC, so.
Yeah.
Ooh, close. It's kind of also funny when it's in that form, it looks like it's stolen out of magazines.
uh, oh, right. So let's plug some stuff in. So we're gonna get so I want to multiply this one by 1 minus or 1 plus x squared. I'm going to multiply this one by 4x. Multiply this one by or minus 4x, I think. I'll add those up. And that's going to be 0. So 6cixi plus minus 4i ci plus I minus 1. And I'm going to split this up right away.
Yep. Definitely the best move.
X to the I minus 2. And one more. Just highlight that. This is I times I minus 1. C I x I minus 2 times x2, which is our signs, right? Okay.
Right, so our x squared gets multiplied by our x to the I minus 2. Add the exponents very nicely. Just get x to the I, which is very nice because that matches up with our first set, which also has an x to the I.
Yeah. Okay. So since those are good already, let's think about them. The first term has 2 extra things than the last term, so we'll take those out to get 6 C0 plus C1x. Um, two. We'll go 6. Yeah, thank you. C I, yeah. Six CI minus I 1 ci xi. Okay. So that leaves the yellow term that you just wrote.
Welcome back, Fen.
Oh, hello.
Hype.
And maybe a red term that I'll write. So.
Yeah, I'll do that one while you, or I guess
Okay,
you can.
fair enough.
Whichever.
Yeah. Okay. Okay. What do I want to do here? I think I see. So let's deal with that orange term. So this is going to be, again, we're seeing that this starts at k is equal to 0, so we'd like to get rid of those first two terms. So k is equal to do we need this? We need this, yeah. Okay, so that'll be minus 4c1 minus 8c2x. Okay, plus 1. Okay. X, okay. And we'll proceed. Plus same plan for the red. It's going to be a k is 0 is 2 times 1. 2c2 plus 3 times 2, 6 c3x plus k plus 2k plus 1 c k plus 2. Ooh, I think I dropped an index there. Let's clean that up. And that should be a plus 1 in the orange. Okay. So
You want to start gathering loose terms, and I'll throw the.
Sounds good to me.
All right. So this is going to be equal to. We'll go with summation I going from 2 to infinity. X to the I times the quantity, and now we'll go from here.
C0 minus 4c1 2c2 plus x times 6c1 from the front.
Suki, the orange, did that need a -4 on the rest of the terms?
It does, yeah.
Okay. And for anybody listening, whether that's outside or inside the summation really makes no difference for us, so we can shift that wherever we need it to go. Oops. changed variables again. Plus. All right, so looking at it from a broader view, we've got 1, 2, 3. Yeah, okay. Looking good, I think.
Okay.
Nice. All right, so again, here we see that the summation starts with I equals 2, and we have x to the I. So therefore, we're going to allow 0 and 1 to just be all of those loose terms, which Stuckey gathered as the constants, and those with x. And so we have those two terms by themselves. And then when we move down, now we want all of the terms that have squares attached to them. So when I is 2, that's going to get us a 6 C2 minus 2 times 1. Is that supposed to be I minus 1? Yes, right, because that's in here. Or no, that's in there. Right. So 2 times 1 is 2. C2 minus 4 times 3. C3 plus, here is going to be 4 times 3. C4. So here we're trying to solve for C4, and that's going to be 1/12 of the following. So moving everything over to the other side, it's going to be a 12C3 plus 2, oops, nope, minus 4. C2, which, based on Stuckey's work above, we also then, that's an interesting combination. Right, this is just going to be 1 C3 minus a third C2. So 5/3 C1 minus 4 C0 minus a third parentheses 2 C1 minus 3 C0. All right, C1 has attached to it 5/3 minus 2/3. That's actually pretty nice. It's just C1. Minus 4 C0 plus 1 C0. All right. It's going to be a minus 3 C0.
Okay.
So it's just always going to be a linear combination of these other two. That's kind of awful, but at the same time, I like it.
Yeah.
So you have here, ooh, that's interesting. C3 drops out completely.
That it does.
That could have some interesting implications.
It's 16, 24. Oh, it's just.
Oh, no. Plus 6 there. C4 I did up there. C1 minus 3, C0.
$22 C1.
C1. Right. 48. 8/5. C0 plus 1/5, so 3/15, just because I'm being difficult. Minus, that's in terms of fifths. That's going to be 1/10. Oh, wait, no. That's 3/5. Which is 11/15. C1 minus 11/5. I was hoping for one of those to switch signs, I think. But no dice for this one. Alrighty. Yeah.
All right.
I don't think I had that as an answer. Oh, interesting.
Because C3 is wrong?
Oh, I hope not.
I hope not, also. That looks solid.
Could be my notes are wrong, so that's fine too.
Sure.
Alright, so we had 2A2, or 2C2, yeah, plus 6C0, yeah, minus 4C1. Where'd that come from? Minus 4C1. Yeah. Okay. I must have done something different in the formulation here. It's fine.
Okay.
Yeah, oh well. At any rate, this is what we got. If it happens to be wrong, then, you know, sometimes that sort of stuff happens, but I'll go over stuff later and figure out what happened. So for right now, we have our initial conditions that y at 0 should be 2 and y prime at 0 should be 3. So if we kind of distill all of this information, we've got that y should be equal to C0 plus C1x plus 2C1 minus 3 C0 x squared plus 5 thirds. C1 minus 4C0 x to the third. And then we can keep going from there. But the more important part is, what do we do from there?
So we can use this to plug in our initial conditions, because if we put a 0 in everywhere, we get all of the terms cancel except for the first, which is supposed to be equal to 2. And if we take the derivative, the first term, the C0 term cancels. The next term becomes C1, and all of the other ones have an X, so those vanish. And this is supposed to be, I don't know, what is it, minus 3? Just made that up? 3.
2 and 3, yeah.
Okay.
Yep. So because all those terms vanish, it makes it very nice to work with to try to get our initial conditions, and that allows us to say, C0, C1 are going to be these values, and therefore all the rest of our coefficients are going to be linear combinations of those things based on the coefficients that we found here. So it's going to make it pretty nice. It takes a little bit of time to actually do it, but, you know, it happens. Okay, and there was one last thing that you had brought up earlier. Uh-oh. And I'm not going to like actually go through any sort of formal stuff. We're not going to actually do any problems on it, but I do want to at least highlight that this thing does exist, and we will be doing some of it later. And that was the Fourier series. I don't know if you want to give it an introduction if you're comfortable with that.
Um,
Your audio disappeared, so.
yeah. Um, right. So broadly speaking, the idea is um, if our function is periodic, or perhaps we only care about it on a short interval, um, then um, it's I want
That's
to
all right.
not lie too much. It's it has an associated uh, series made up of sines and cosines. Um,
Yep. So generally speaking, right, we're going to say that this is again, either periodic function or close enough. As you said, if it's over a very short distance and the period is longer than that, then we don't have to worry about it so much. But generally speaking, very much like the Taylor series, where we're trying to find a group of polynomials, which I guess technically group of monomials, which when added together to form an infinitely long polynomial, end up approximating our particular function better and better and better with every step that it goes. If there are a literal infinite number of terms, it can replicate literally any function. It just takes a while to do it. And we have to make sure that our function is still going to have appropriate domain over the given area. We can't start, again, we can't start working with negative values for our Taylor series expansion for a natural log. Even though natural logs, right, have absolutely nothing to the left of nothing in the real domain anyway, to the left of our, yeah, for any negative numbers that you plug in, we could, in theory, plug any negative numbers into any polynomial we wanted. So, like, what's the problem? Well, it's because the domain isn't the same. So the same stuff applies with our Fourier series. Again, if you're over a short enough domain, it's fine, it'll work. And if you're on a periodic function, it'll work rather nicely. But more or less, the way that this breaks down is that f of x can be approximated as, and then when you bring all this stuff together, we can, in fact, make it equal to the terms a sub 0 over 2 plus a series made up of k going from 1 to infinity, a sub k cosine of kx plus another infinite series. B goes from, or x goes from 1 to infinity. of b sub k. Man, we're acting up today. Sine of kx. So in theory, we should be able to find a sum of sines and cosines, which are going to find, as we get more and more terms, better approximations for. And then if we go literally out to infinity, a perfect match to any function we want. This then uses sine and cosine functions, which have shorter and shorter and shorter period lengths and higher and higher and higher frequencies as k gets much bigger. So we can highlight a little bit of this in a couple of weeks after we talk about a, let's see, next class I have us doing Laplace transforms. And, oh, no, sorry, next class, 2 days, not next week. Have us talking about Laplace transforms, and then probably might be before the end of class, but definitely at least next Monday we'll talk about Heaviside functions and how Laplace transforms will apply to differential equations. All right, I think we're probably good for today. Unless you want to do another example or have one in mind.
No, I think I'm
good. All right. So everybody who is in chat, thank you again for coming around. We're going to give yet another shout out here to Ian Stuckey, who is going to be doing the No Royal Road blog.
Yeah.
And looking at it, sorry, you can go. You can explain it better.
Sure. I mean, broadly, I'm thinking about geometry and sort of the basics of algebraic geometry right now. And this is a sort of formative step because I've just learned what a sheaf is for like the fourth time, and this time I think I actually kind of understand it. So I'm trying to record this understanding somewhere so that I don't lose it again.
Completely, yeah, completely fair. So much stuff I've lost. All right, so I think Stuckey will probably let you go for the night, and thank you for coming in and being a co-host on the show.
Sounds good. Thank you for hosting.
Yep, no problem. See you later.
See ya.
All right, and for the rest of us here, we're going to, again, we're going to stay here. Anybody who wants to, you can ask any questions you want, whether that be about our differential equations or whether that be about any other mathematics that you want to talk about. So feel free to line up your questions, throw them in chat. If not, we will look at maybe a couple of other questions that are in Discord, see if anybody's got anything interesting going on there. We'll see how it goes. Woo! So I'll probably give it a couple of minutes here for anybody who has a question, and then if not, we'll probably take our break after that. Before we go hunting. Alrighty. Oh no, it's the last of the coffee. I did want to say that in terms of my gaming the last several weeks, I have forgotten to mention something that I keep wanting to bring up. Currently, and as of July 2024, uh, the SAG-AFTRA in the United States, which is the union for Screen Actors Guild, has called a strike on all video games due to the fact that the industry is not properly paying. Let's see, this time I think it was especially motion capture, hours worked, and localization teams that have worked all around the world to get games properly translated into different regions and the dialects that generally will support somebody's understanding of what's being said in the game. So the localization teams have not been paid terribly fairly, and I believe mocap has not been paid fairly for hours worked. And as such, SAG-AFTRA went on strike over the summer. They did, however, say, do not stop playing games because you are still supporting the people who made them. What they would like you to do is just to highlight anybody who is streaming games. They just want you to highlight the fact that this is a thing. SAG-AFTRA is on strike, and the members, the people who are actually working on the games, are going on strike for the localization teams to get their appropriate pay. So, essentially, no change for streamers. Just, highlight the fact that this is a thing that's going on. Alrighty. I'm not seeing anybody calling for anything. So I think we're going to take a quick break then, cycle some water, maybe grab a snack. And then go over to the Maths forum and take a look at any questions that have not been any questions that have not been addressed. There we go. Addressed is a good word. So thanks everybody for sticking around. We'll go for a 3-minute break, and then we'll stay on for another hour or so. Try and support some people doing their mathematics, and we shall return. Thank you very much. Alright, we're back. Sorry about that. Just had to do one last little thing. My kid lost a tooth, so I had to sneak in with a pound coin. Question. Can we actually play Pretzel Rocks, or is it gonna not work for us again? Okay, well, we might be able to get at least one track out of it. See how it goes. Okay. I'm gonna give a shot at punching. You have here. Find the volume of a solid, which lies between the planes perpendicular to the x-axis at x equals -4 and x equals 4. Cross sections perpendicular to the x-axis are semicircles whose diameters run from y squared equals, no, x squared plus y squared equals 16 is the realistic way to do that. Okay. Solid lies between planes perpendicular to the x-axis. Oh, I should probably also, I suppose, take pictures of this before I get too involved, because otherwise I'm not going to do it, so. And a 1. Here, 4 here, and 5 here. Cool. Alright, we're going to stop that session and reset the canvas. You're worried you're taking pictures? Or somebody's taking pictures of you? Oh, I suppose you probably also don't have Linux in your daily life, so there's a good chance you don't have that particular soundbite. Today is hashtag not sponsored by Beavertown Lupuloid IPA. It's a very strange one. Do not age. Drink fresh. Store cool and upright. Oh no. Okay. Best before April next year. Okay. Very pale. Our glasses from the College of Engineering and Physical Sciences at UNH contain negative 2 to the 4th e to the I pi ounces. Well, you know, all that Twitch money. Affords a certain level of certain level of notoriety. What am I doing? Right? Let's. Okay, Pen. We're gonna take a picture. Really? There we go. Alright, so we got here our X, Y, and Z axes. But which is which? Oh, right. Get rid of the sloppiness, because we don't need that. I can appreciate what they're trying to do, but not today. Alright, so if we go X, Y, and Z. Okay, -4 and 4. Cross sections, semicircles whose diameters run from y equals so this is going to be a circle that runs like that. Cross sections perpendicular to the x-axis are semicircles. Whose diameters run from... Okay. Whew. Okay. That took a minute. Okay. So we got something that looks like this. Right? Only better. This is awful. Something like that. Right, so this surface is running down like this. And back down to 0 there. And it's expanding out as it goes this way. And then starts decreasing here. Goes back down to there. Is this just a hemisphere? No, probably not. But interesting thought. Okay, so we want a solid that's running like this, right? Every time that we pick 2 points, which are across the circle from each other, we draw a semicircle which goes across like that. Oh man, terrible. It might be, and it could very well be. I haven't proven it, so therefore, right? All right, so the way that we want to do this is we want to say we're going to take a dy slice like this and find the volume of this three-dimensional solid based on these individual slices. Now, right, punching, it would be helpful to know what class you're in. I suspect you're in either Calc 2 and you just started, or, well, right, that was one of our first sections that we did in Calc 2. Or possibly Calc 3, and they want you to shift and to start using, like, multivariate calc. I don't think triple integrals are going to be the way to go yet, though. Okay, so z... Yeah, we don't need to do this. Everything can be done in terms of x and y, and in fact, in this case, in terms of y only. Right? So we need summation of the individual areas of these semicircles. This is completely kosher notation, I promise you. All right, I is going to go from 1 to n, and this is going to be taking the limit as n goes to infinity. Times dy. Delta, okay, delta y at first. So the way we should be looking at this, if you're doing this for the very first time, is pretend that each one of these things is like a cookie that's taken out of a block of wood. So we've got like a log that is just a semicircular prism, right? You just take a semicircle and you just continue it as long as you want. This would be a terrible approximation for this particular solid, but it's still better than nothing. It'd be a good, like, first guess. All right, then we say, okay, this is not a good one. So let's get a couple of, like, larger semicircular prisms, stick them next to each other, and then we can start, like, stacking them up to get their approximate heights matched up. And, you know, the volume will be approximately that. So we start cutting the thickness down of each of these individual logs, and we got logs of all different sizes in order to make all this work. So here, what do we need in order to find the volume of each one of these things? So it is a semicircular prism. Or a half cylinder. Now the point really is that the half cylinder is going to have a height that is really, really tiny. Or at least as we start moving through this. So our radius here is our x value, which is going to be the same both up and down. So that takes care of both our x and z directions. It's just all encompassed in x. That's it. Okay. Yeah, you know what, Pen? I think it is. I think it is just a hemisphere because the y values are going to be linked to the size of our x values as well. Unless we're completely wrong about it, and that's perfectly fine by me. Right, because every time we cut through a sphere, we're going to get a cap that has a cross-section that is a circle. Right, anywhere you cut through a sphere, you get a circle. Asterisk. No, okay. I think I'm right. Okay, so volume is going to be equal to area times height, which is going to be pi r squared times the height, which is going to be pi times x squared times the height. Height is dy in this case, or delta y. So the thickness of this thing is going to be our delta y, the change in our y value. So, question, right? If yeah, okay. I think it is a hemisphere because then we can take this from 0, 0, 0 and link this out to, I mean, literally any point, but if we do it along, the y-axis, right? That's going to get us our y direction here and our z direction here, which, if we follow that all the way around this semicircle, right, we should get here the same location there, but now this is still our y direction, and this is our x direction. So those should be the same. Next question, is the y value the same as the x value? Because that's going to be helpful. Can we prove that? Okay. So for every point along this, and I mean like literally every point, then we know that x squared plus y squared plus z squared has to be equal to r squared. If we're already on this circle, that cross section oh, I'm rotating 90 degrees, but the principle's still the same. Right, perpendicular to the x-axis, not parallel to. Well, you know what? There's only one thing that could be done with that. Ta-da! Fixed. All right. So actually, these are backwards then. I want to say that the reasoning is actually pretty easy. And we should be able to say, yeah, look, these are all going to be the same. Our x's, our y's, our z's. If they're along this particular circle, then x and y should be essentially interchangeable. All right, each of these semicircles is itself a circle that is in the, no, not x. Boo. Y squared plus z squared equals like r1 squared, whatever that's going to be. So I'm probably overthinking this. It's fine. I mean, like, anybody else has any brilliant ideas, let me know. No, okay, never mind. I was trying to do something over here, but that involves like y squared plus z squared, so that doesn't make any sense for what we're actually trying to do, which is replace our y squared term with a function of x. I mean, right, is it always going to be 16 minus x squared is equal to y squared? Or is that just along the perimeter? Let's just try it. So if we assume that the volume is going to be limit as n goes to infinity of the summation as I goes from 1 to n of our volume slices, which are going to be pi times y is going to be the square root of 16 minus x squared parentheses squared pi r squared times delta x. As n goes to infinity, our volume becomes the integral from -4 to +4, x equals, of pi times r squared is now going to be just 16 minus x squared times dx. This is going to be equal to pi times here 16x minus 1/3 x cubed, evaluated from -4 to 4. Good enough. All right. Is going to be pi times the quantity of 16 times 4 is going to be 64 minus 1/3 of 64, right? It's 4 cubed. Is going to be 2/3 64 and pi out front. Okay, minus parentheses 16 times -4 is going to be -64. Right, and same thing's going to happen on the other side, so we end up getting a plus. Okay, I'm happy with this answer. Sort of. Something else is going on here. Plus a 1/3 times 64. Alright, so it's going to be a negative 2/3. Negative, it's going to be a plus 2/3 times 64. Oh, it's half of a... It's a semicircle. That's way better. Very silly. Right, which is equal to a half times 4/3 pi 4 cubed. And wouldn't you know it, that is half the volume of a sphere, or the volume of a hemisphere. So yeah. So, punching, there you go. So you got 2/3. Yep, 2/3 pi r cubed. Yep. Yes, the symmetrical version, that drops some of the terms, does make the integration easier. I would explicitly explicitly lay out the formulaic solution first. So in the case of what I was showing down here, right, the end, we ended up with volume is 1/2 4/3 pi r cubed. That's the volume of the hemisphere. That gets your teacher to recognize, hey, You understand what's going on here. I would explicitly lay out the formulaic solution first to highlight the fact that you see it as a hemisphere, then state the exact value, then state the approximate solution if asked. Hopefully you did in fact see it was a hemisphere. Okay, so there's an interesting issue with this next one that I see. So I took this from the next problem. It is the fraction x minus 3 over x plus 3 is less than 2x minus 1. And both Penn and Alex at this point and both Penn and the person who asked went through, and by the way, if you have any questions, you can post them into Penn Center's Discord. I'm totally selling his Discord out because I don't really have one, but or rather I have one, but it's mostly just for my like friends at this point. It's like just for the purpose of me having one. Man, I don't even have the TKF banner in my bio. Like, I need to work that out. Okay, so both the student and Penn at this point said, let's multiply both sides by x plus 3. Now, under most circumstances, I would not care about this. Timestamp on my stream is... Nope, not that one. Not that one. That one. Boo. There we go. 239. Alright, so my problem with this is that if x plus 3 is less than 0, then we need to switch the inequality direction. Now, both Penn and the student did this, but they resolve it later on. So my problem is that if you say, okay, x plus 3 is less than 0, you're going to have to switch the inequality direction, And when does that happen? Okay, well that's if x is less than -3, right? x is less than -3. Which maybe it doesn't come up, right? Maybe it's fine. Maybe it doesn't matter. But I don't want to create a solution or a situation where this is relevant at all. So what I'm going to do is I'm going to say, okay, let's pretend for a moment that this is x minus 3 over x plus 3 is equal to 2x minus 1. And if you want, we can even put a little asterisk above the equality sign, which says, really, we don't want this. We want the thing that's up there, the less than inequality. But for now, we're willing to put up with putting an equality sign in there so that we can figure out where it is going to be equal and where we're potentially going to have problems. So if we do this, then we say, let's multiply both sides by x plus 3. And keep in mind, right, I was a coordinator for my pre-calculus program for 15 years, or, well, 12 years. Right, I taught pre-calculus for 15. So, like, over those years, this is what and almost constantly taught pre-calc over those 15 years. So this is just what I have worked out over the years as kind of like the best method of explaining what exactly is going on with all this stuff. Alright, this multiplication is going to give us 2x squared plus 6x minus 1 is going to be a plus 5x. And minus 3. Right, add 3 to both sides. And subtract x from both sides. We get a 2x squared minus plus 4x is equal to asterisk 0. So at this point, we know that we're going to have potential solutions if we factor out a 2x at x plus 2 times 2x equal to 0. Now, what is this? Well, if we look at the structure of how all of our rational functions, which is what this x minus 3 and x plus over x plus 3 is, what we're saying is these are the places where our signs can switch by these two functions being equal to each other. So in some transformed world, if it shifts a little bit, we can end up finding out that these are the zeros for this transformed function. What happens at zeros? Well, that's where functions change from positive to negative or negative to positive. They could have other behaviors, right? Staying positive, or staying negative. But in this particular case, we're seeing that the multiplicities of the zeros in this particular function is 1. So all of our multiplicities are 1. Therefore, it doesn't really matter. It doesn't really matter in terms of like what kinds of behaviors we're going to see. They're all going to be going from negative to positive or positive to negative. In the original function, x minus 3 over x plus 3 is equal to 2x minus 1. This is where that rational function that's doing this, or maybe this, I guess, is crossing through a linear function. So we want to know, where is it crossing through the linear function? Well, this is how we're finding it out. So where is it going to be crossing from below to above or above to below? Right, this is telling us that 2x is going to be equal to 0 or x plus 2 is going to be equal to 0. Again, technically, this is just what we're looking for. We know it's not really equal, but whatever, it's fine. So x is going to be at either -2 or 0, crossing through our linear function. So those are places where we can end up switching signs. Right, so this is where it switches position, either above or below, compared to, okay, the two functions switch position. Right, above or below each other. So most likely we've got something that looks like -3, right, something like that. And then this is a 2x plus 1. This is a terrible drawing, but, you know, pretend for a moment. Right, we've got intersection points between these two functions. They switch from being above and being below each of these points. Right, looks something like this, roughly speaking. I don't know exactly. Whatever, it's cool. Was it 2x minus 1? It was. It was 2x minus 1. Ooh. There we go. Alright, so it looks something like this. Give or take. So they're going to swap position, again, above or below, at those 2 points, x equals -2 and x equals 0. Then we've got to say that, well, this can also switch position anytime that we have a discontinuity. So this is talking about our, kind of like our intermediate value theorem? No, the other one. Well, somewhat, right? This is showing that, like, for the continuous parts of this function, so from -3 until infinity, and from -infinity until -3, these behaviors have to match. Right? If we're going to be on this branch above y equals 2x minus 1, and there's no intersection point between that curve and that line, then they're never going to change positions with each other. One will always be above and the other will always be below, because both functions are continuous on that interval from -infinity to -3. And they never intersect, so therefore they can't change their positions. But the second we have a discontinuity at x equals -3, this could potentially change from being above to being below. And that is what we find if you actually just graph this, right? So we can say here that if you actually graph it, right, you get this nice 2D graph, which is pretty obvious what happens. If you just want to do a 1D graph, then we're going to include -2 and we're going to include 0 as our 2 points where they could intersect each other and therefore change position. Then we have to include all potential discontinuities. So x equals -3 x equals -3 is a discontinuity because at the beginning we had x plus 3 in the denominator. So realistically, right, from a pre-calc point of view, we want to take this aside and say, okay, x plus 3 cannot be equal to 0. So we end up with x cannot be negative 3, or x equals 3 is a discontinuity. Yep, I saw your mark there, so I'll get back to you in a second here, punching. Okay, so we have a discontinuity at x equals negative 3. We have zeros at x equals negative 2 and x equals 0. Or rather, again, not zeros of the function, but where the two functions intersect each other, right? Intersection points. Their distance between each other is 0. And we wanted this to strictly be less than, not less than or equal to. So we've got to leave those open, right? We don't want those points. We want the points where they're strictly above and below each other. Okay. Now we say we've got x minus 3 up top over x plus 3 is less than 2x minus 1. Now we just go through here and we say, give me test points. So give me a point that represents each of these regions. Let's go with easy numbers. So 1, negative 1. This one's kind of a pain, but whatever. Negative 2.5, it's fine. And negative 4. Right? Have these represent each of those regions. Because again, intermediate value theorem, if we don't have any discontinuities, and those functions never equal each other, then they have to be on the same side as each other throughout that entire region. So between negative 2 and negative 3, negative 2 is the intersection, negative 3 is the discontinuity. Every value in between has to have the same truth value for our inequality. So if we plug in 1 into both top and bottom, 1 minus 3 is negative 2 divided by 4, so negative 1/2 is less than 2 times 1 is 2, minus 1 is 1. So negative 1/2 is less than 1. I'd say that's true. All right, now we should predict that negative 1 is going to be false. So negative 1 minus 3 is going to be negative 4. Divided by negative 1 plus 3 is 2. So that's going to be negative 2 is less than 2 times negative 1 is negative 2 minus 1 is negative 3. So negative 2 is less than negative 3 is false. Right? And if you want to write it out, right, be explicit about it and state like, hey, I plugged in these values, this is what I got. Clearly this is false, so we're going to cross it out. Clearly this one, right, this one was true. Negative 2.5 is going to be a negative 5.5 up top divided by a 0.5 down bottom. So that is a negative 11 is less than negative 2.5 times 2 is negative 5 minus 1 is negative 6. So yeah, that one's good. And then negative 4, we go with negative 4 minus 3 is negative 7, divided by negative 4 plus 3 is negative 1, so that's going to be a positive 7, less than foreboding. Negative 4 times 2 is negative 8, minus 1 is negative 9. So that's false. So the regions for which this work, this has to be an open circle at negative 3 because it's a discontinuity. It has to be an open circle at negative 2 because we can't be equal to each other. And it has to be open at 0 because it can't be equal to each other. Shade in the appropriate regions. So the places where we had successes. So our x values that have acceptable values are going to be between negative 3 and negative 2 exclusive, union with 0 to infinity exclusive. Come on in here tomorrow. Tuesday nights are my usual math nights, so I will be available for whatever. Trig was one of the classes that I coordinated as a part of pre-calculus. So, yeah, my trig is say less. Eh. But if you want to just get like online resources, you know, Khan Academy is pretty good. They are tutoring, so if that's what you need, it could work. There's a bunch of other ones that are online, so you could find Paul's online notes, like Purple Math or something like that. Didn't go in depth enough. Okay, yeah. So, like, SalCon's great for being a tutor. Basically, it's, here's a skill, let's show you how to work the skill. And, yep. And so, like, I prefer to teach people how things work, and Sal is much more interested in showing people, like, how to get from a question to an answer in the fastest way possible. And pedagogically, I disagree, but I can understand that most students don't really care about like the like the why of how a problem works. They care about trying to finish a problem. And whether or not they can perform said problem. As I said, I disagree. I think that getting at least people who are interested in understanding why things work is more important at a fundamental level. We actually did one a few days ago, where we were trying to like integrate some, you know, something with a square root at the bottom. I don't know, like, I don't even remember, 36 minus x squared. Maybe there was an xdx up top, something like that. Uh-huh. So I'm just making this up. I have no idea if this is going to work, but there's a couple of ways of doing this. One is you look at this and you say, what trig functions do I have that can make this nice? Right? So here, I would probably want a 6 squared minus something squared is equal to something else squared. So, in terms of like trig functions, right, I'm doing, this is 6 squared times the quantity 1 minus 1 over 6 squared, and all this stuff squared. So then I'm going to want to have something in here which is going to get me a sine squared theta. Right? So what do I put inside the blank in order to make that work? Well, that's going to be like 6 squared sine squared. Oh, well, okay. 6 sine theta. right? Which, when squared, is going to knock out all this stuff and eventually make something a bit nicer. So we get a 1 minus sine squared. This is going to get us a 6 squared cosine squared theta, which then makes it much nicer to work with. So I don't always see these particular integrals, especially integrals, that are coming out of this stuff. Oftentimes I'll look at this and I'll be like, I gotta tell you, I can't remember. So instead of going this route, where I'm like, what should I plug in for x? You know, let x be 6 sine theta, and then this is going to work out. Right? Let's say for a minute that I don't remember. I can't reason it out just that way by coming up with a trig identity. So what I would often do is say, well, this thing here is going to tell me that our 36 is going to be the hypotenuse of a right triangle, or rather the hypotenuse squared of a right triangle. So I'm going to draw out a right triangle with theta, and our hypotenuse is going to have a length of 6, which gets squared to 36, and then we're subtracting x squared, which means that one of the lengths is going to be x. And then the length of the other one is the square root of 36 minus x squared, right? It's the thing that you've got. If you ended up with, you know, integral, and down here is the square root, and you've got, you know, 36 plus x squared, or something like that. dx, I don't care, whatever. Right, then this thing is going to say that we have the same right triangle, or rather, it's not the same right triangle. This is telling us that our two legs added together are going to be when squared. So we get 6 for one leg, x for the other, and then the hypotenuse is square root 36 plus x squared. Right, so what do we do with these? Well, in the case of our, in the case of this one here, we can say that the tangent of theta makes the much easier relationship. It's x over 6. Over here, we're going to say that the sine of theta makes the easier relationship, also x over 6. So I prefer to make diagrams, because in this case, now I can say, well, okay, yeah, x is going to be 6 sine theta. Like, obviously, you just do some algebra. And down here, we get that x is equal to 6 tangent theta. And again, it's trivial. It's super easy when you do it that way. It might take a little bit of work. It's not terrible. In this case, we also have x and dx up top. So our x is just going to go in as 6 sine theta, and our dx is going to be 6 times the cosine of theta d theta. So this one, a bit different. This stuff is going to make integral of 6 sine theta d theta up top. Oh, nope. Oop. 6 sine theta times dx, which is 6 cosine theta d theta, over square root of... And actually, in this case, this is another thing that you could do. You could look at this triangle and say, well, our relationship, actually, even better. I can go one further. I can make a relationship this way. Yeah, that's even better. Wow. Okay. So here, this says that the tangent of theta is equal to x over square root 36 minus x squared. Now, I don't know if this is actually going to make this any better. I think it is. It's probably fine. Right? So this says that instead of all this stuff, we've got now the integral of the tangent of theta times d theta, which was 6 cosine theta d theta, or dx. Dx is 6 cosine theta d theta. Tangent is sine theta over cosine theta. 6 out front, integral. And then we were multiplying by cosine theta d theta. So cosine theta is gone now. And we just get 6 integral sine theta d theta. So much easier. I didn't need to mess with all those fractions and stuff. Just clean this up. Right, we could have always gone back and said, oh, well, we're gonna just plug in 6 sine theta in for x, and then like algebra our way out. But I don't appreciate that too much, right? It's gonna be messy. I'm gonna make mistakes, so of course my students are gonna make mistakes. I don't want to subject everybody to that. That's just mean. Okay, so x over the square root was our tangent of theta, and then our dx was 6 cosine theta d theta, so we've got that. The 6 is out, the sine's there. We take the integral. This is now going to be 6 times... Are you serious? Add... Apparently we're on an ad break because it didn't give me enough time. Didn't give me enough warning. Alright, so we'll give it 2 minutes. And I'm going to eat a cracker. I'm allegedly on an ad break. Or maybe you just came back. Right. So going back a bit, we said that 5 seconds. Okay, so going back a little bit, we said that we can clean all this stuff up by just saying that the tangent of theta is going to be x over the square root of 36 minus x squared, which is literally inside of our integral here. Right? The ratio between x and the square root of 36 minus x squared is literally right there. So that's the tangent of theta. we go in and we put that in. We get this integral of tangent of theta times dx has been transformed into 6 cosine theta d theta. Our cosines go away. We just get the integral of sine of theta d theta, which is negative cosine of theta plus c. Our cosine is then, therefore, here, the square root of 36 minus x squared divided by 6. So we just throw that back in for the cosine of theta. Square root of 36 minus x squared over 6 times the 6 that we already had. Those go away. And so we get the negative square root of 36 minus x squared plus c. So this is actually not too bad for something that I just made up on the spot. Most of the time when I make up Calc 2 problems, they go horribly wrong. So this is generally what I like to do, is I like to pull out all of the, like, 20 different ways that I've learned how to do stuff over the last 15 years that I've been teaching, and attempt to get to wherever you are in your understanding. So, if it's working, awesome. Can't always guarantee that I can help every single person in every single, perspective. No, we're not doing this? Cool. I'm glad you liked it. If you have any other questions, let me know. Because we can, if there are any particular ones that you're just like, yeah, no, I hate this. Yep, no problem. So Monday, Wednesday, lately have been class, and so we're doing our differential equations class. Afterwards, I'll take whatever questions anybody has, provided that I'm feeling up for it. Tonight's pretty good. We'll see how I'm feeling on Wednesday. And tomorrow night, Tuesday nights generally, is our math night, so I will just be doing general help for anybody who wants it, popping over onto various Discord servers and looking at who wants any sorts of questions, or who has any sorts of questions, who feels, who feels particularly responsive in their either their posts or if they're literally in chat like you. Hey, that we could work on stuff. But yeah, I don't know. I think that this has been good overall. And we'll try and get some more interesting, cool stuff for anybody who has any other questions. But I think tonight this is probably gonna... I just took an ad. That was silly. No, hang on. First exam Friday from Stuart. Okay, cool. So I never actually took a class from Stewart, like the original calculus. My spouse and I both took Calc 3 out of Stewart, and she might have done Calc 1 and 2 out of Stewart, actually, now that I'm thinking about it. But, did I? Let's say 2001. No, we didn't take it with this one. Who did we take it with? Wait, I thought I saw it. Oh, is that it? That might be it. Larson. His original calc book, Calculus with Analytic Geometry, was... it might be a different... That might be a different one, but... yeah, there's a very particular, like, ring sort of thing that he's got on his... version. Yeah, okay. Larson did my pre-calc book back when we were with Pearson. Yep. In my high school, we had Larson, I want to say like 3rd edition or something like that. There it is. Early transcendental functions, Larson, Ostetler, Edwards. Yep, they're the same people who did, they're the same ones who did our pre-calc. 1999 hardcover. Yep, that's the one. So it's not, that's not exactly what I'm talking about. So it's not exactly, right? This, right, it's not, the shell and washer method. This is a 3-dimensional shape that, like, they created using, I think Larson did some sort of research into this, and then created this surface, which is, again, wild, like, strange donut sort of thing. This is, like, it's got multiple thicknesses to it, and it's sort of like a Mobius strip in that it goes around on itself. I don't know how to explain it really well, but it's essentially a 3D Mobius strip, and there's something else going on with it. But it's defined by some interesting characteristics. So there's some cool stuff that's going on there. But so yeah, that was my calc book in 2001. Then we had the same one at college. What? That's just weird. All right. Hmm. Struggling grad student. Is that his Twitch handle? Or YouTube handle? Which, like, mood? Um... Yeah. I know several struggling grad students who have been on YouTube over the years. Tibby's is a good one who's out there. She is Australian and had been... I can't remember if she was at Melbourne or if she was in the UK for a bit. But... Porque no los dos. But she ended up dropping out of her grad program because it was just like, I think she lost sight of why she was doing it. It was just kind of like, I was doing it because I just wanted to do it and not because it was fun. It stopped being fun, and she was just like, this is not working for me. She did a locked-in scenario, or actually she's done a couple, where the only entertainment that she brought on a train with her on like a really long ride was math, and so she set goals for herself to learn certain things by certain stops, and her producer, and I don't know if this is her partner or just like, you know, somebody on her team or whatever, gave her exams at like certain stops to see if she really knew what she thought she knew. And then she also did one where she was locked in, and I do actually mean locked in, to a RV. So she was locked into an RV, and the only thing that she had was I think, topology or something like that. And so she had to learn certain things by... I don't remember exactly. It was like once every 6 hours she would get an exam. And then she had to... if she answered the first one right, she got... like... electricity or something like that. And another one she got... I can't remember. It was like, you know, you have the privilege of using these things. So, Waffle, that's so being locked in, or having a lock-in, is when a bunch of students are usually, you know, literally locked into a building or something like that. Hey, Bertram! A bunch of students are locked into a building, so they're not allowed to leave. Granted, if there's an emergency, they're allowed to leave. It's fine. But, you know, they're not allowed to leave the building. So this was like our after prom and after graduation. We had a lock-in where we went to a particular venue and we just had like activities that were going on all night. It was kind of cool. Ours was done at the Whittemore Center of the UNH, on the UNH campus, which had a bunch of like gym rooms, which are normally reserved for, like, you know, there's a couple of basketball courts, there's a couple of squash courts, there's a track that goes all the way around on the bottom floor. It's only like 100 meters long, and it's like, you know, square oval. the corners are rounded, but and a weight room and like several side rooms that had movies playing and things like that. So that was our post, I want to say that was post grad. So after graduation we went there to just hang out all night. The theory was that we would be doing that, which would be hanging out with our friends for one last time before we go off into the world, rather than going out drinking. So it was especially good in my town because so many people did not go anywhere. Boy. I get the feeling that several people would have just grabbed like a 24 rack and hit the beach. So like in our town, not literally everybody knows everybody, because I was part of a high school system that had one central high school and 6 surrounding towns that all sent kids to the central school. So we didn't know literally everybody, but realistically, I knew probably about 40 to 50% of the people in my town by name and by sight. That I could have said, oh yeah, that's this person from that place. And I wouldn't be able to tell you their address, but I know exactly where they lived. I didn't know, like, a lot of the older people especially, unless they went to my church, went to the town hall meetings, or like worked in town somewhere prominent. Then maybe I'd know who they are. But, you know, somebody who was like 65, just randomly, they keep themselves to themselves, I don't know who they are. But yeah, being near being in a town whose population is still under 2,500, right? That's it's pretty amazing. My spouse was also from a fairly small town in Maine, which was also like just up the street from where I was, pretty much. It was about, I mean, it was about 30, 40 minutes away. But like, yeah, we didn't know each other. We were a significant distance apart. It's not really that surprising. We weren't part of the same communities or anything like that. So there's the possibility we could have met like years, but what is this? Possessed by Dave Hewson. We're gonna skip. Swing Fever. Yeah. So like there's a possibility that my spouse and I like had passed each other in the mall or gone to the same movie theater or something like that, and a fairly decent chance. But like we wouldn't have noticed each other ever. All right. Anybody have any questions? Interesting queries? General math is tomorrow. So that's 9 o'clock BST, British Standard Time, which is, let's see, you are West Coast Bertram, so that is going to be 1300 or 1 o'clock PM. If you have class during that time or something, then I'm terribly sorry. I'll throw another one out here just because. Oh, you're East. Yeah. Yep. Nice. I mean, yeah. But East Coast of the United States. Yeah. Whereabouts are you now? Generally. Yeah, I can do some linear algebra, so it depends on what you need. If you want specifically, like... If you want some crazy hard thing, then probably not, but, like, if it's Jordan form, what is span, that sort of stuff, then we can gauge where I'm at, where you're at, and try to meet in the middle. Alright, so let's do this. 16.4, take the natural log, this is 2.797. 33 natural log is 3.497, and 38 natural log is 3.638. Okay, let's go with 6, 3, 2, 1, 4, 5, like that. And 4 on that end. Wait, wait. No, that's fine. Right, we can do a natural log as a linear distance. That's fine. I thought we wanted a log scale, but we do not want a log scale. We want to just take the natural log of these numbers. Length and angle stuff. So, polar form. Doing vectors. So that's, yeah, you're right at the beginning of the semester, of course. Orthogonal vectors and projections. Yeah, sure, we can try. Alright, so we get 2 by 2.7. 2.8, give or take. 4 by 3.5-ish. And 5 by 3.6-ish. Okay, you have the following data points which belong to a function of the form y equals a times e to the b over x, where b can be positive or negative. You wish to determine the value of the constant b in order to construct a linear plot, give or take. From the values of x and y in the table above, calculate the values of the 3 corresponding data points. Click on the graph below to use Freeform Curves tool and plot the data. Line segments will automatically connect the points. What is the numerical value of the constant b? I have absolutely no idea. However, let's see. If we do this with Desmos, go with table 2, 3, 4. Nope. 5. Get rid of 3. Yeah. Function natural log 16.4. Natural log 33. Natural log 38. Okay, y is approximately equal to, so we do the tilde thing. A e to the b over x, x1, y1. Okay, r squared is 0.9997. Numerical value of the constant b is going to be negative 0.87981 based on Desmos. Now the question is, how do we calculate this? Y, no, b over x is equal to, okay, so b is going to be equal to natural log of y over a times x value is 4.34 for A. When do we hit 4.3? Just out of curiosity. Y equals A. Is it asymptotic to A? It is, right? Because your exponent can never be 0. Alright, so it's asymptotic. Alright, so where do we get that from? So we want to know, how do we get... Right, where 4.3 is an asymptote. Man, with only 3 data points, that's really rough. Alright, I'm going to put forward a question to the poster to ask what class is this for and what values, or do we have a procedure that's actually like available to us to see what they're trying to do? Because as much as I like fumbling around in the dark for answers, I'm not sure exactly how this one works. So it's interesting, but not something I could really spend a lot of time on without context. Okay, I think we're gonna head on over to somebody. Gonna see if anybody's doing any math at the moment. High Potential is currently doing some chores and watching James May. I mean, sure. Ooh. Rogan is currently working on Chance of Senar, which is an awesome game. Oh, Dr. Gold's on, doing actual education, or doing science and tech. Yeah, we'll go see Dr. Gold. There's also somebody who looks panicked as though he is inside of a math class himself. As always, Irish John Games is currently working on some more Rise of Piracy game dev. Paleontologizing is working on Dinosaur Q&A, and Astro Canuck is waiting for some astrophotography. So needs to be dark enough in his sky in order to actually do anything. So usually ends up being a while, especially since I'm in the UK, so it's quite a time difference. Alright, so I hope that everybody is having fun. And we're going to head over to see Dr. Gold, doing some more, looks like SAT prep, but could be other stuff too. Yeah, no problem. Thanks for coming on over, and I will see everybody tomorrow. We'll do some more math help type stuff for general audiences, not just our, like, differential equations people, whatever. And then we'll be back on Wednesday for differential equations. Freaking Mexican hat dance. And then we'll be back on Friday for gamey type stuff. We'll see what I'm feeling like. But have fun, everybody. See you later. My name is Obi. Have a good night.